Setting up a reaction table for a pH calculation with a common ion. So this is essentially how you can solve for the pH of a buffer solution the long way round without using the Henderson-Hasselbalch equation. If you find this a little tricky, my advice is to write out two balanced chemical equations. The first one being for the dissociation of your acid. So you're going to work out what the conjugate base of the acid is. And the second one for the complete dissolution of the salt. So you're going to assume salts are soluble in aqueous solution, and that equilibrium position lies 100% to the right. So you're going to use one of your all the way to the right arrows in that case. So let's go ahead and do that. So again, it doesn't matter what the formula of the acid is, because we know generically for a weak acid plus water, that is going to the acid will donate its proton to form whatever its conjugate base is. So that's just going to be the anion that is left after you remove the proton, and water is the other product. So I guess I'm being really naughty here and leaving off my state symbols, so I should put those on. AQ and H2. 3O plus will be my hydronium ion. That's talking and typing for you. AQ. So then if I draw in my correct arrow here, equilibrium, like so, comme ci, comme ça. Let's do that in blue, because otherwise that would be unusual. Okay, so that is an equilibrium situation. So let's do that for our actual acid that we have, propionic acid. Even if you've never heard of it before, don't know how to say it, have to keep looking at the formula to work out what is going on here. You know it's going to be a proton donor, and we conventionally tend to write the ionizable proton on the front of the formula. So if I lose a proton from this, I'm going to lose an H and subtract one from the charge. So I'd call that the propionate anion, but that's by the by, we don't have to name it. Okay, so now we have our dissociation of our weak acid. We can do the same thing if it's a base as well, right? We know how to do that. If it's a base, it's a proton acceptor, so you just stick a proton on it, H+. Okay, so what about our salt? So our salt is sodium propionate. Again, you don't even need to know that. So remember, when we write the formula for the salt, we write it pretending it's a molecular compound, but it isn't really. If it's a soluble salt, it's going to completely break apart into the cation component, usually the metal, so Na plus Aq, and then whatever's left is the anion component, so C2H5CO2 minus. So you do have to watch with stoichiometry for these, okay? Because sometimes a salt might have, more than one cation or more than one anion, and we're just going to do it 100% all the way to the right arrow. So if we compare these two aqueous reactions that are happening at the same time, we see they have something in common. They both yield this propionate anion. So this is what is called our common ion. So it is the conjugate base of our weak acid, and it is also the anion that is liberated by the salt. So we can now say that this is a basic salt because it's liberating the propionate ion, and this is the propanoic acid is the weak acid, and this anion is its conjugate base. So they have this ion in common. That's our common ion. So the only difference when we are doing an ice table is that we are going to acknowledge that the starting concentration of our conjugate base of our weak acid, because it is a common ion with the salt that's completely dissociated, is going to have a non-zero starting concentration. Okay, and then we're just going to fill out the ice table in the normal way. In terms of what the concentration is, well, if we are 0.38 molarity in sodium propionate, and if we have 1 mole of sodium propionate, is going to dissociate to give us 1 mole of our propanoate ion, however you say it, then that's a 1-to-1 ratio. So the concentration of our conjugate base is going to be equal to the concentration of our salt in this case. So you may have to do a stoichiometric calculation, but in this case it's 1-to-1. So we can start filling in our ice table. The initial concentration of our weak acid is the 0.42. Our initial concentration of our conjugate base is 0.38. That is coming from the salt, and we are assuming there's approximately 0 concentration of hydronium to begin with. Then you're just going to fill out the rest of it like a normal ice table. So minus X is representing the ionization of the weak acid, plus X is the formation of conjugate base from that ionization, and plus X is the formation of hydronium from that ionization. So then you just add down each column to get your final concentrations at equilibrium in terms of X. So the only thing that is changing from what we normally see in an ice table is that we have, in this case, 0.38 plus X instead of just X for the concentration of our salt at equilibrium. So then you're just going to stick them in the Ka expression or Kb expression if it's a weak base, right? And of course, we can't actually go ahead and solve this because we do not actually have the value for Ka, but just like you'd do normally, so it's going to be the concentration of our conjugate base times our concentration of hydronium divided by our concentration of our weak acid, C2H5, CO2, I had to look at it as well. So you're just going to stick those numbers in terms of X. And if we knew the value for Ka, we could solve it just like we do with a normal ice table. The X is small approximation. Obviously, you should check that it is valid. But, I mean, the action of our buffer solution, the presence of that common salt, according to Le Chatelier's principle, remember that old chestnut, right, is actually going to really inhibit, let's say, the ionization of that weak acid, because if you think about it, it's the same as having an excess of product in your reaction mixture. So if you have an excess of product, I'm talking about this guy right over here, you got too much on the right hand side of the equation, it's going to shift the equilibrium to the left to favor reactants. So we're going to have a very small ionization of our conjugate base at equilibrium due to the presence of the common ion. So the X is small approximation really is going to work the majority of the time, which is why the Henderson-Hasselbalch equation is so useful, because for a buffer solution, usually you can just go ahead and assume X is small, and if you can use X is small, you don't have to do all this rigmarole, you can just go straight into the Henderson-Hasselbalch equation.